Hello. In the last of these videos, I introduced the radial distribution function as a way of probing the structure of a system. If you have read the example report that you're working towards in this block of the module, you will have seen the following figure that shows the radial distribution functions at two different temperatures. You will also have read in the text that accompanies the figure that the RDF on the left is the RDF for a solid, while the RDF on the right is the RDF for a liquid. To summarize the exercises thus far, we have seen that the radial distribution function offers us with a way of probing structure, a way of distinguishing between systems that are in the liquid, solid, and gas states. The question that I want to probe in this video is if there are other better ways and better forms of analysis that we can use for this task. In other words, is there a better way of determining whether a system is in a liquid/solid state? The answer to this question is obviously yes, as there would be little point in making this video if these other methods did not exist. If these methods did not exist, I would tell you to compute the RDF and we would be done with it. Consequently, without further ado, let's talk about how these other methods work and what they offer in terms of analysis that differs from what we can do using the RDF alone. At the heart of these alternative forms of analysis is the notion of a symmetry function. These symmetry functions have the general functional form shown here. We can calculate one symmetry function for each of the atoms in our system. To understand this formula, we thus start by drawing the red atom to indicate the position of atom I, the central atom for which we are computing the value of the symmetry function. Next, we draw these blue circles to represent all of the other atoms in the system. Notice that we perform a sum over all these other atoms in the formula. Furthermore, Rij in this expression is used to indicate the vector that points from atom I to atom J. These vectors are indicated by the black arrows in our diagram, and we are summing over all of them. The sigma in the product inside the sum here is a cutoff function. This is a function that is 1 when the vector Rij has a magnitude that is less than a cutoff, and that is 0 otherwise. The vectors that satisfy this condition of having a magnitude that is less than the cutoff distance are indicated by the black lines inside the circle. The circle represents the cutoff distance. When we calculate the symmetry function, we are thus calculating some function f using the vector that connects the central atom to each of the atoms in its first coordination sphere. Once we have calculated these f values, we then add them all together. In other words, f is just a function of the x, y, and z components of the vector that connects atom I to atom j. Often we will choose f so that it might look something like this. For the function shown here, f is large if the vectors connecting the central atom to the first coordination sphere point along the particular directions where the blue and red nodes of this function are contained. So it's large if the vectors point into the blue region or the red regions. What I'm trying to get at here is that symmetry functions can be used to determine if the vectors in the first coordination sphere point in particular preferable directions. In other words, we are searching for bonds that point along certain directions, which is the behavior that you would expect in a solid. You would not expect to find this sort of orientational order in the first coordination sphere around the atoms in a liquid. Symmetry functions thus have a large value for atoms that are part of a solid and a small value for atoms that are part of a liquid. It is important to note at this stage that the symmetry functions for the atoms will not have one particular value when the system is in a solid state and a second different value when the system is in the liquid state. You would expect to find symmetry function values in all symmetry function values in all the different states of matter. What will change, however, is the distribution of symmetry function values. In this exercise, you are thus going to calculate the distribution of symmetry function values from a molecular dynamics simulation. The steps in this procedure are as follows. You will first calculate a particular symmetry function, the FCC order parameter that is explained in the instructions to the exercises. You will do this for all of the atoms in the trajectory frames. You will then use all of this data to build a histogram that indicates the distribution of order parameter values that was found from the simulation. Notice that you can converge this histogram pretty quickly because, much like we saw when we were calculating the radial distribution function, you can average over all the frames and all the atoms in all the frames when computing the histogram. This works because the atoms are all indistinguishable, and you would expect the distribution of FCC order parameter values to be the same for each atom in the system. The final step that you are going to explore in this exercise involves getting the free energy as a function of the FCC order parameter using the formula shown here. Notice that what emerges from this formula is an energy that is a function of a coarse-grained variable. In this case, the coarse-grained variable tells us whether the atoms are in a solid-like or liquid-like configuration. We can thus, in theory, use this free energy surface to tell us the free energy difference between the solid and liquid states for the conditions at which we performed the simulations at. This idea is important, as this business of plotting the free energy as a function of some order parameter of interest is a technique that is regularly used in papers on atomistic simulation. It is thus good that by completing the exercises and the assignments, you are getting the opportunity to try doing this for yourself. I hope that you've given you enough information in this video to complete these exercises and the assignment and do this particular form of analysis. Thank you for your attention and good luck.